Hello friends, welcome back to the tetrahedron chemistry classes. So guys, in the continuation of lecture series on coordination chemistry, today I am going to take Jahn Teller distortion or Jahn Teller theorem, right? So what actually happens in this Jahn Teller theorem, this is there in this slide. So what you can do, you can focus on this middle structure, this particular one, right? In the center you have the metal ion. You can have any metal ion here, and then you are having your 6 ligands, and I have marked these ligands as L1, L2, L3, L4, L5 and L6, right? And this center picture is actually the situation of the regular octahedron. Regular octahedron means you have say this kind of the complex. Okay, say if I put the model in this way, you can understand, right? Now it is very clear to see. 1, 2, 3, 4. These are the ligands, 4 ligands which are in present in the xy plane, and this is the ligand which is above the plane, right, which is in the z-axis, and similarly this particular one, this is also in the z-axis, but it is say below the plane, right? So if you see, the structure is just like that. And in this particular case, if you measure the bond length between this central metal, see, you can assume here in the center metal is there and all ligands are there. See, two, one is above the plane and one is below the plane, 4 are in the plane. All the metal ligand bonds length should be equal if your geometry is perfect or the regular tetrahedron. That means no distortion is there in that case, right? So this is the picture which I have depicted here. This one, regular octahedron, all metal bond length are equal, and whenever you have say the complexes in which the electronic system is just like that, D3 electronic system or a D5 electronic system, and similarly you can have D6 electronic system in the complex which is having the lowest spin complex, and you can have the D8 system in any complex, right? That means the 8 electrons are present in the d orbitals, no matter whether the complex is low spin or the high spin, right? There would be no Jahn Teller distortion in that case, and whenever these systems are there, you will have the regular octahedron geometry and all bond length should be equal, right? Now we will see what the distortion actually is. So what I can do, say this is the ligand number 6, this is the ligand number 1. What I can do, if I hold these two L1 and L6 and I moved away these two ligands from the z-axis, right? I am taking away these two ligands. You can think in this way, if this is the way a ligand is situated here, I am removing this ligand by extending from this z-axis, right? So what happens when I move the ligands from from this complex L1 and L6? So I am removing. So what actually happening in that case? The length actually increasing between the metal and the ligand N1 and the metal and ligand L6. So these two bond lengths are actually, you can see they are the increasing one, while these bond lengths, remaining bond lengths would decrease. So in that case, you can see the elongation of this z-axis is actually taking place. So this is known as the Jahn Teller elongation, because we are lengthening the bond length of these two L1 and L6 ligands which are attached to this metal. So this is known as the tetragonal elongation. Why the name is tetragonal elongation? See, when this distortion occur, when we have actually extended these L1 and L6 from L6 ligand from this central metal ion, if you see through the z-axis at the top, right, then you will find, okay, it is look like something tetragonal in shape, right? So how the tetragonal shape looks like, you can understand in this way, right? This is the actually clear picture, right? This was the z-axis, and we have moved these ligands away. And when we move these ligands away, obviously these 4 ligands which are present in the xy plane, they would come closer to each other. That means these two bond lengths would increase while rest 4 bond lengths would decrease, right? So this was the tetragonal elongation. So again you can see here tetragonal elongation, because we are moving the ligands away from the z-axis. This tetragonal elongation is also known as the z-out tetragonal distortion, or simply the z-out distortion. In that case, bond length between the metal and the ligand L1, which is this one, would be equal to the metal and the ligand L6 bond length. That means these two bond length would be equal, and these two would be greater than either this metal L2 or metal L3 or metal L4 or metal L5, which I have written here, right? So this is actually the distorted octahedron, sorry, distorted octahedron, and this is tetragonal elongation or Z out, right? And generally whenever you have, it is however it is not always necessary, but whenever generally if you have this d4 electronic system, that means the complex in which d orbitals having the 4 electrons, then this tetragonal elongation is observed. Okay, this was the first case. Now think the reverse situation. In the first case, I have removed these two ligands from the z-axis. Now in the second case, what I will do, I will press or I will compress this bond length. See, I am pushing this ligand L1 towards this metal ion, as well as I am pushing this ligand L6 towards the metal ion. So what will happen? Their bond length would decrease, right? So when their bond length would decrease, what happened? These bond length would increase. Sorry, I have to actually make or see, I have to make changes in this one actually. So say, now forget this one. So I have moved L1 and L2 towards the metal ion, which I have written here. So they are going towards the metal ion, and when these bond lengths are decreasing, so these bond lengths would increase. Okay, so they are going outside. So in that case, you can see what happens. Compression is there because we are compressing the ligands present in the z-axis, that is L1 and L6 ligands which are present in the z-axis, we are compressing them, right? So this is known as tetragonal compression. And compression means actually this is Z-in type of distortion, because we are pushing the ligands in the z-axis. We are not taking out from this axis, but we are pushing actually, right? So how the situation look like, you can think in this way, right? This is the way actually. If you compare these two, right? If you compare these two, then you will quickly observe, okay, these two bond lengths are quite large in that case, but here these two bond lengths are actually the smaller one, right? When these are smaller, obviously these XY plane ligands will have the higher metal ligand bond length, which is this is known as the compression. I have written here, you can see compression and elongation. Okay, so what happens in that case, if you see the metal and ligand L1 bond length would be equal to the metal and the ligand L6 bond length, and these two would be lesser than these, whether ML2, ML3, ML4 or ML5, right? And this tetragonal compression, which is Z in type of the distortion, is actually observed in the D1 system, right? Actually observed in the D1 system. So you can see in the D1 system, we can have this Z in type of Jahn Teller distortion. In D4 we can have the Z out type of, right? In D3, D5, D6, D8 we will not have any kind of the distortion. But in between them, if you have the D7, D8 and D9 system, then it is almost impossible to predict whether actually the distortion is Z in type or Z out type. It is not possible to actually identify. Okay, so this we have done already. Now in the previous slide I have explained what is actually the Jahn Teller distortion or tetragonal distortion. Now the question comes, why this Jahn Teller distortion occurs, and how Jahn and Taylor, see, these are the two separate scientists, Edward Jahn and your Herman Taylor, they both actually contributed to this one. So what their theorem says that any non-linear molecule. See, in this particular lecture, we will discuss all octahedral complexes, but it is not necessary that your complex should be or should always be octahedral. It could have any non-linear type of the geometry, right? So the statement or the theorem is just like that: any non-linear molecule in its electronically degenerate state. Right? Later we will come what is the electronically degenerate state. Electronic degenerate state means whenever your electron can have more than one arrangement in the orbitals, right? So any nonlinear molecule in its electronically degenerate state would be unstable, right? And to gain the stability, it will undergo the distortion, and when it undergoes the distortion, it will remove its electronic degeneracy. When the electronic degeneracy removed, then the energy of the system would be lowered, and also the symmetry of the system would also be lowered, right? Definitely the system symmetry of the system would be lowered, because from the perfect geometry we'll move to the distorted geometry, and distorted geometries are actually not very higher in the symmetry, right? So this was the theorem actually. So in this case you can see the electronic degenerate state. So we have to understand what is the meaning of the electronically degenerate state. So electronically degenerate state means whenever your T2G or EG, see if you are taking your octahedral geometry, then T2G or EG, if they are unsymmetrically filled, then it is known as the electronically degenerate state. So what is the meaning of this? You can see here, I have this D1 system. You may have the see hexa aqua titanium complex actually, where D1 system is there. Then obviously if you have only one electrons and the splitting would occur in the octahedral complex, then obviously in the octahedral complex T2E would have the lower energy and EG would be higher. This I have explained in my previous lectures, the crystal field splitting in the octahedral or tetrahedral and the various kinds of the fields. So you can go there, right? I am giving you the link in the description if you haven't seen those video, right? So you have only one electron, and this one electron is here. I can put this one electron in the dxy, but on the other hand I can simultaneously remove this electron from dxy and put this electron into dyz. So this is another arrangement, and then I can put this electron into dzx also. So three different kinds of arrangements are there for this one electron in the T2G set. That means this is electronically degenerate state, and because it is unsymmetrically filled, right? Unsymmetrically filled means uneven distribution actually, right? So this is known as the T2G, electronic triply degenerate, and it is indicated by the small t. Okay, then moving to the next one, if you have the D2 system, then obviously your two electrons would go into the T2, and then you can put these two electrons here. But in the while putting in this dxy or dyz, you can give the different arrangement also. You can put the electrons in these two orbital dxy and dzx, and then again you can have the different arrangement also in the dxy and the dzx, right? So again three arrangements are possible, triply degenerate. So it is also the degenerate state. That means when this happens, right, whenever the condition is this one, then definitely your complex would be unstable and it will undergo Jahn Teller distortion. Okay, and similarly, say for example I have written D4 here, but I haven't written D3 here. Why I haven't written D3 here? Because I have already told you in the D3 case there would be no octahedral no Jahn Teller distortion, so I haven't written that D3 here. While in case of the D4, right, so D4 you can have this particular situation, high spin complex. See, if your complex is high spin, and you know the high spin complex would be there in the if you have the weak ligand present in the complex, right? So what is the meaning of the high spin? We will have all the electron paired, because in that case you can see the pairing energy would be very high, so electron would not pair, rather it will unpaired in the two different sets, T2G and the EG. So this situation you can have this is symmetrically filled, it is non-degenerate, it is non-degenerate. When symmetrical filling is there, then it is known as the non-degeneracy. But in that case, in the EG orbital, you are having only one electron, it is actually a degenerate, right? Why? Because one electron can go into dx square dash y square. If I can write this as dx square dash y square, or it can go into the dz square. So again, two different kinds of arrangements are there for this one. So however, Jahn Teller distortion in that case would not be there due to the presence of these electrons, but the one electron present in this EG set would cause the distortion, and it is electronically doubly degenerate state, which is indicated by E, right? And similarly, if you want to go, then you can go for the D4 low spin complexes. In low spin complexes, pairing energy would be low, so electrons would get paired up. So in that case, 4 electrons, 1, 2, 3, and the fourth one. But again, I can shift this fourth electron in this one and fourth electron in this one. So we can have again the different arrangement of the electrons. So it is non-degenerate state. So it is again T, because triply degenerate. Similarly, you can go for the D5, and same explanation would be there for the D5 also. Whenever these situations would occur, then definitely your Jahn Teller theorem would be there, and you will have a different distorted structure for the complexes. Okay. Now next is the you can see the prediction of your distortion. See whether distortion would occur or it would not occur. It will purely depend upon the the system actually. So if you have the say D1 system, so you know in the D1 system you will have this T2G set, okay, and then you will have somewhere in higher energy the EG set, which is having this one. Because the electron is only one, so you can put one electron here, okay, and when you can put this one electron here, then it can have the three different kinds of the arrangements, as I have shown already to you. In that case, 1, 2, 3 different arrangements are there. That means in that case, Jahn Teller distortion would occur. So it is liable to Jahn Teller distortion, right? And on the similar ground, you can see here, I have explained this. If you have the T2 electronic system, again these three arrangements would be possible. That means in that case also the Jahn Teller distortion would occur. Okay, now coming back to this one, say this is your T2, and somewhere here you will have your EG. So you are having 3 electrons, 1, 2, 3. So in that case, you can see the symmetrical arrangement is there. It is electronically non-degenerate. So in that case, Jahn Teller distortion would not occur. In the D3 system, you will not find any kind of this Jahn Teller distortion. Now you can have your D4 system, right? So D4 system I have already explained to you, right? So but it is necessary to write for this D4 system. So how I can write for this D4 system? Say first it is my low spin complex. Whenever I will have the low spin complex, that means the electron would be paired up because the pairing energy would be high. So these are the 4 electrons, and somewhere here you will have your EG also, right? So degeneracy in your T2. If you have the high spin complex of same system, then what would happen, right? I can write in that manner. So how many electrons are there? 4, 1, 2, 3, and the fourth one. So now I have degeneracy in the EG set. So in that case, of course, the Jahn Teller distortion would occur, and in that case, the high spin complexes also the Jahn Teller distortion would occur. Now what is the difference? See, if the Jahn Teller distortion is happening in both the cases, then what is the difference? The difference is that whenever your electronically degenerate state is present in the EG set, then your Jahn Teller distortion is very, very high. So in that case, very large or very high magnitude of Jahn Teller distortion would be observed, right? Because we are having the electron in the EG orbital. So what will happen when we have the electron in the EG orbital? You can recall the shapes of the d orbitals. These EG sets actually are, if you know, this is your say dz square, if we can recall, right? And then this was your dx square dash y square. They are along the axis. Whenever the EG set is there, when dz square or your dx square dash y squares involved, orbitals are involved, so they are actually directly see these orbitals are directly in the path of the ligands, and ligands would exert more repulsion when the electron present in these orbitals. So this will lead to the higher actually splitting and also the large Jahn Teller distortion. So you will remember this particular point if you are deciding the two systems in which one Jahn Teller distortion would be higher and which one would be lower. So you will see the electron where the electron is present. If electronically degenerate state is present in the EG orbital, then your say Jahn Teller distortion would be very high. Okay, then you can have your D5 system. So again, in case of the D5 system, you have the two situations. So in say if D5 system is just like that, I have written here, say this is my EG, sorry, this is T2G, this is EG, this is T2G, it is EG, and say my complex is the high spin complex, right, in presence of the weak ligands present in the complex. Then 1, 2, 3, 4 and 5, I can fill 5 electrons just like that, right? So in that case you can see it is non-degenerate state because only one arrangement of these electrons are possible. You cannot have another arrangement, right, because symmetrical distribution is there. Similarly, in that case electronically non-degenerate state is there, only one arrangement of these electrons would be there. So whenever this happens, no Jahn Teller distortion. So D5 system where the complex, where your high spin complex, no Jahn Teller distortion would be there. Now coming back to the D5, say low spin. Okay, whenever it comes to the low spin, then definitely your 5 electrons would be like that, 1, 2, 3, 4 and 5, right? And of course your T2G EG would be there, but this would be empty, right? So this D5 low spin would have, see, if you can rearrange, this electron can come here making this one singly occupied, this electron can come here making this one singly occupied. So 3 different arrangements are there. It is electronically non-degenerate state. Of course Jahn Teller distortion would be there, but that distortion would not be very high because it is happening in the T2G, and T2G orbitals are actually in between the axis where no ligands are actually approaching from this particular direction. Okay, so now coming back to the next one, say D6 one. So again in that case, if it is D6 low spin, right, if D6 low spin is there, so I can write 1, 2, 3, 4, 5, 6. You know, in the low spin all the electrons would be paired up. So again you can see the electronically non-degenerate state, that means no Jahn Teller distortion in D6 low spin, right? But if D6 high spin would be there, right, so you can write 1, 2, 3, 4, 5, 6. So in that case you can write just like that. So this is what electronically non-degenerate state. So your distortion would not occur due to this one, but here you can have the degeneracy, electronically degenerate state, because 3 different arrangements would be there in that case also. So again since this distortion would occur due to the presence of this T2G, right, electron present in the T2G, so distortion would be there but not very high. It's not very large. Okay, now coming back to the D7 system. Okay, D7 system are, say, something special. Say I am taking this high spin, I can write just like that, right? So 1, 2, 3, 4, 5, 6, 7. Okay, so this is the situation just above one, D6 or D7. They are actually having same kind of the situation almost, right? Again it is actually the non-degenerate one, so distortion would not occur due to this, but the distortion would occur due to this one, because it is, again, it will have the 3 different arrangement. So distortion would occur, but again the distortion would not be very large, because it would occur due to the T2G set. Now if you go for the low spin, D7 low spin, then D7 low spin will have this kind of situation. 1, 2, 3, 4, 5, 6 and 7. So it is electronically non-degenerate state T2G1. So due to this T2G orbitals, right, there would be no distortion because this is symmetrical distribution, non-degenerate. But in this EG case, this is degenerate state. That means having the unsymmetrical filling, that means doubly degenerate, distortion would occur. And since the distortion is happening in the EG, electron present in the EG orbital, so this distortion would be very, very large. So D7 low spin would be very, very large. If you go for the D8 system, so there would be no distortion. D8 system, there would be no distortion. You can fill the electrons, right? If I have just like that, okay, now I have to fill say 8 electrons. Say high spin I am taking 1, 2, 3, 4, 5, 6, 7, 8. So this is symmetrical distribution electron, this is symmetrically distribution electron, non-degenerate, so no distortion. If you go for the say low spin, this was say high spin, and then if you go for the low spin, so again you have to fill 8 electron, 1, 2, 3, 4, 5, 6, 7, 8. Both situations are same. So in that case, D8 system, you will not observe any kind of the distortion. Say if you can recall, I have already given this to you. In the D8, whether a low spin or the high spin, there would be no distortion. I have already pointed out this particular point. Okay. So if you have the D9 system, then definitely D9 system would have the distortion, and you can fill the 9 electrons in it. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is non-degenerate because symmetrical distribution of electron is there, but this is actually your say unsymmetrical distribution. This is electronically degenerate state. Now this would do the distortion, and this distortion again would be very, very high, very, very large or huge, right? So in that manner you can predict. See, D4 system, high spin, very large distortion. Similarly, you can have this D7 low spin, very large. D9, whether low spin or high spin, doesn't matter, very large. In some cases there would be no distortion, but while in other cases there would be very, very less distortion. So in that manner, if you know what is the oxidation state of your central metal ion in the complex, then you can calculate the total number of electrons present in the d orbital. And once you find the d system, how many electrons are there in the d orbital, then you can easily predict which kind of the distortion, whether it would be high or low, you can predict, right? So this was actually the crystal field splitting, right? This is the crystal field splitting. In case of here, say crystal field splitting in the Z out or the tetragonal elongation, right? So what we are doing in the Z out, if you can recall the situation of just like that, you can recall this was L1, this was L6, this is L2, L3, this is L4, this is L5, right? These were the ligands actually, and we are removing them, right? We are pushing them out from the Z axis, the Z out. That means the ligands are not present in the Z axis very close. So the electrons present in the, see, metal is there. Say this is the orbital which is present in the see, these are the orbitals which are having say metal electrons. Now there would be repulsion between metal and ligand, but if you are pulling these L1 and L6 away from this one, so definitely the repulsion would be low for the orbitals which have the Z component, right? So what happens, you can see this was actually, see, if I have started here, this was the d orbitals in the free metal ion, and this was the say hypothetical situation, d orbitals in the spherical field, and this is the crystal field splitting in the octahedral field, right? But as I already told you how actually we can form this elongated or distorted geometry, by either pulling these electrons from this z-axis or pushing these ligands into the z-axis, right? So it is always it is always better to start with this diagram actually. So when we are removing the ligand from the z-axis, obviously the z orbital of the metal would feel the less repulsion, and you know that when the repulsion is less, the energy of the system would be lower. So these two would actually see they are the degenerate one, but after that they will remove their degeneracy. When they remove their degeneracy, so this dz square would have the lower energy, because ligands are not actually there in the z-axis, while in the xy plane we are not doing anything, or moreover they are coming close actually. They are coming close in the xy plane, so this dx square dash y square would have the higher energy. Similarly, this is your T2G set. Again, it is actually the degenerate type, but it will remove the degeneracy in the distortion, and again it will split. Since the z from the z direction we are removing the ligand, or we are pulling the ligand away from the z axis, so definitely the z orbital containing, the orbital containing the z component would have the lower energy. So in that case you can see dyz and dzx, they will have the lower energy, and dxy would have the higher energy, right? If you want to calculate the splitting, so again already I told you the trick actually. If you are calculating for this one, so you will total count these two. If you are calculating for this one, then count this. How many numbers are there? 2. You can write 2 here, and total orbitals are 3 here, so 2 by 3. If you are calculating for this one, so you see this one is there, right? And total orbitals are 3, so 1 by 3. So actually this dxy orbital is actually raised in energy by this factor of 2 by 3, while dyz and dzx would be lowered in energy by this factor of negative 1 by 3. So this is the crystal field splitting in the Z out or the tetragonal elongation. If you reverse the situation, right? Say if you reverse the situation, then it will give you the tetragonal compression. That means this would go up, this would come down, and these two would go up and this would come down, and that would result in the tetragonal compression kind of thing. Okay, so I have though I have given here, you can see I have given here, right? So now in that case, in the second case, what we were doing, what we are doing actually, again I am taking this slide here. So we are compressing these two towards the metal. That means they are coming close to the metal. So the orbital which have the Z component now will feel the more repulsion, because the ligands are coming very close, right? When the repulsion is high for the orbitals containing Z component, so their energy would be high, right? So the splitting would be just like that. You can see again they will remove the degeneracy, but this dz square in that case would have the higher energy. Okay, because we are pushing the ligands towards the metal ion, and these orbitals actually lying along the axis, so this will have the higher energy, and this will have dx square dash y square will have lower energy. Similarly, this z component are there in the dyz dzx, they will have the higher energy, and this will have the lower energy dxy. And again you can, if you are calculating for this one, so count this 2 by 3 of negative, 1 by 3 of negative. So this is the situation actually, right, for z in. So this was for z out, and this was the z in. If you compare these two, you can see here the reverse situation is there in the cases actually. So what is the advantage of doing this one actually? The advantage is that you can easily predict whether actually elongation is happening, or your say compression is happening. For example, if you have say D1 system, you can take this example. If you have the D1 system, and you are focusing say on compression, so obviously your electron would come here. Okay, and if you are focusing on say elongation, so your electron would come here, right? Now if you calculate the energy for this one, so this would be 1 into negative of 2 by 3. Okay, and this will give you somewhere around negative 0.6 7. And if you do this one, negative 1 by 3 into 1, so that will give you somewhere around negative of 0.33. If you compare these two energies, then you will find negative 0.67 actually is lower than negative 0.33. So energy is lower in that case. When energy is lower, obviously the system would get the more stability. That means this would be Z in or compression type of distortion would be there when you have the D1 system, because it is energetically more favorable. And whenever we are actually whenever we are deciding, or we will decide whether the Z in or Z out would be there, it is always better to calculate the energy of the system, right? So in that D1 case, compression would be there. So in the slide I have already written here, you can see, if you focus here, in the Z in distortion, D1 system I have mentioned actually, and the reason is that we can calculate the energy very easily. I think this is fine, right? Now say, moving to the next one, which is, see, Z in and Z out is clear, distortion is clear. Now another very important aspect is there, right? Which is known as the static Jahn Teller distortion or dynamic Jahn Teller distortion. So what is the meaning of the static and the dynamic Jahn Teller distortion? I have summarized the points here. What you can do, you can take the snapshot of this one, so this would be easy for you to understand. Okay, so first I am explaining the static JT distortion, that is static Jahn Teller distortion. See, this static is actually temperature independent. No matter your temperature is high or temperature is low, this type of say distortion would always be there. This is the first point, right? And if you compare the dynamic one here, see, this dynamic Jahn Teller distortion would be observed only at the low temperature. This is very important, the first point of difference in these two actually. Now the point number 2, no matter whether your complex is present as salt or is present in the solution, it doesn't matter, static Jahn Teller distortion would be there in case of the solid as well as in the solution. Okay, this is something very important, right? And third point, EG orbitals are electronically degenerate, leads to the static. See, whenever very large JT distortion is there, large JT distortion is there, so large means actually the static one, because it is the strong one. And and you know the strong distortion would occur whenever your EG orbital is electronically degenerate. Okay, so this will lead to the Jahn Teller. Okay, but when you have, say, T2G are degenerate, T2G orbitals are degenerate, that means you will have the weak type of the distortion. Okay, and second thing, you can very easily predict. You can see here I have written two complexes here. In that case, your NO2 is the ligand. In that case, cyanide is the ligand. These ligands are very strong. When your ligands are strong, then this is the hint actually. However, it is not 100% correct actually, but whenever the ligands are strong ligands will always lead to the Jahn Teller distortion. Okay, not always, right, but lead to the Jahn Teller distortion. But if your ligands are weak actually, see, if ligands are weak, then Jahn Teller distortion would be the dynamic type. Okay, so I have written here in this complex AC weak distortion, T2G are degenerate, and of course the weak ligands are there. You can see these complexes. Water is weak ligand, so they are causing this one. Okay, and see, observed in the complexes where splitting is large. See, static Jahn Teller distortion would be observed in those cases where actually the splitting is very large, and you know, in the light of the crystal field theory, only then your crystal field splitting would be very high, than when you will have the strong ligands. Okay, and in that case you can see here, when weak ligands are there, the crystal field splitting would be low and the distortion would also be low. So dynamic distortion is actually the weaker one and this is the stronger one. So what is the difference actually? What happens actually here? See, what happens in this one, whenever the distortion is weak kind, so what will happen, see, this Z out kind of distortion would occur, and simultaneously for the same complex Z in kind of the distortion would also occur, and these two would be present in the equilibrium. So they are actually going back and forth in the from Z out to Z in, right? Coming back and forth, Z out, Z in, Z out, Z in, Z out, Z in. So if you do the physical measurement, then we will actually we will get the result that like that we are actually having this perfectly symmetrical tetrahedron. So that's why it's it is a general assumption, and it is not the general assumption, it is the fact that this dynamic Jahn Teller distortion is not easy to predict with the physical measurement. Why? Because we have the average symmetry of the molecule, and the average symmetry of the molecule is the regular tetrahedron. Okay, so I have written in at this point, in this fourth point, in these complexes thermal energy, see, if you keep your complex, if your solution in your say at room temperature, so the molecules will have the sufficient energy, sufficient thermal energy, and this thermal energy is actually doing this one, Z out, Z in, and they are in the they are in the equilibrium, thermal equilibrium, right? So equalize the population of the complex ion. In this complex, thermal equilibrium, equalize the population of the complex ion, elongated and the compressed one, and as I have explained, thus physical measurement detects an average structure, and average structure is the perfect tetrahedron. Okay, and this happens in your say the complexes where we have the weak kind of the ligand. So this is the difference between static and the dynamic Jahn Teller distortion. It is very, very important to understand actually, right? So I hope this is clear to you. So guys, this is actually all about your Jahn Teller distortion. Now very quickly I will explain some of the problem which has been asked in the previous year CSIR NET and the GATE examination, and if time permits, then I will explain few more problems to you so that you can have the better idea about the Jahn Teller distortion and as well as its application, where to apply actually. So okay, this is the question from CSIR NET December 2013. You have given two type of the complexes, complex A this one, complex B this one. In both the cases, if you see here in the both the cases, right? See, if I can write here, Cu NO2 6. Okay, and both the cases you are having actually the 4 negative here. Why 4 negative? You can see the 2k, that mean, see, if you ionize this one, then you will have the 2k positive plus Ba, which is barium 2 positive. When 2 positive, 2 1 are 2, 2 plus 4 positive are there, you have to put 4 negative here, right? So 4 negative means copper is in +2 oxidation state. So whether you take this complex or this complex, in both the cases the same situation would be there, and the question is that the unpaired electron in A and B are found respective. So guys, you have to see, however it is given in the question, these two complexes exhibit tetragonal elongation as well as tetragonal compression, right, respectively. That means this one is giving actually elongation, right? So you can write elongation for this one, elongation, and this one is giving the compression. This one is giving the compression. Okay, and now you have to find whether in which orbitals the single electron would go there. So for this you have to know what this Cu2 positive is. You know, copper 2 positive is actually having the 27. See, copper is having the 29 of atomic number. If you remove the 2 electron, you will have the 27 electron, and for 27 electron it is actually 3d9 system. Okay, so it is actually the 3d9 system. So how I can explain this one? I have to search the paper. Okay, now, right, so D9 system. So first I am going for this elongation, and if elongation is there, then you have to fill 9 electrons here. So 1 2 3 4 5 6 7 8 9. So in the elongation case, right, you are having electron, see, whenever the elongation is there, so your unpaired electron is present in the dx square dash y square. Okay, now if you do the compression, this is for compression, 2 3 4 5 6 7 8 9, where the electron is in the dz square. So in that case the electron is in dz square. So you can check the answer here. So dx square dash y square dz square, your option number B is the correct answer. So in that manner you can solve this particular problem. Okay. Right, this is the next problem taken from the CSIR NET June 2014, right? So the complex is like that. Identify the correct statements about this complex and this complex, right? So you have given 4 options. So actually you can see they actually asked about the bond length. So whenever they are asking about the bond length, so you have to predict whether the Jahn Teller distortion is happening or not. So in that case you can see the nickel is in +2 oxidation state, and nickel having 26 electrons in that case. See, atomic number is 28 for this nickel. If you remove 2 electrons, it will give 26, and 26 means it is 3D8 system. Okay, this is 3D8 system, and water is weak ligand. Okay, when water is weak ligand, that mean the complex would be your high spin complex, right? This I have explained during my previous classes actually. So if you want to fill the electrons, so this was your T2G octahedral complex, splitting would be just like that, 2. So you will fill 8 electrons, 1 2 3 4 5 6 7 8. So see, this is degenerate state, this is non-degenerate state, symmetrical distribution. This is also non-degenerate state, symmetrical distribution. That mean in this nickel complex no Jahn Teller distortion. And you know, when no Jahn Teller distortion would be there, all bond lengths would be equal. All bond lengths are equal. So you can see all nickel oxygen bonds are equal. So this may be your answer going to this one. Nickel O equatorial, and see, this cannot be your answer, right? All nickel and bonds are equal, whereas CO bonds are equal. This could be your answer. And all CuO, while nickel bonds are shorter. No, nickel cannot be shorter because all bonds length should be same. So D cannot be your answer. Okay. Similarly, B cannot be your answer. So you have to select between A and C, right? Now if you go for this copper 2 positive, it is 3D9 system. Okay. Whenever the 3D9 system is there, okay, so you can have this kind of situation. 1 2 3. Okay, again it is a weak ligand. 4 5 6 7 8 9. Okay, so electron is present in the EG, so very large distortion. Okay, whenever the distortion is very large, so what will happen, this whenever this splitting would occur, this say where I have, okay, say this is the one situation. You can have your electron here, but that is tetragonal compression, and then you are having the tetragonal elongation. Your electron is in the dx square dash y square. So it is up to you from where you want to put this electron by considering the energy factor. So you can see what would happen. In that case, distortion would be there, and copper equatorial bonds are shorter. Okay, this could be explained very beautifully. Okay, so see, H2O is here, H2O is here, and in the central nickel is there, and rest all H2Os are there. In that manner you can write, right? So in that case, this should be elongation. This is higher in, this is say higher bond length. this bond length would be higher. So option C, bond length C, whereas CuO equatorial. See, this is copper, sorry, this was copper actually. So these are the equatorial bonds and these are the axial bond. So axial bonds are longer, equatorial bonds are shorter. Okay, equatorial bonds are shorter. So here I have written CuO, it is given here CuO equatorial bonds are shorter than Cu axial bond. So C could be C is your answer. It is given in the CSIR net answer key also. But the problem is that how will you identify whether this elongation has taken place or your compression has taken place, because in the D9 system it is not easy to predict. So what argument I can give you, the simplest argument is I can give you, say this was the situation and I put electrons here just like that. Okay, so electrons 1 2 3 4 5 6 7 8 9. When the splitting would occur, so this will come here, this will go there, so one electron is here and remaining 2 electrons would be here. Okay, and when this happens, then again I can write 1 2 3 4 and 2 electrons are 5 6. So this is d yz dzx and this is say dz square, this is dxy and this is dx square dash y square. So I am taking say elongation. Why I have taken this elongation? Whenever the distortion would occur, you can see here the energy of these 2 electrons would be, see you can see here this distortion, 2 electrons are actually lowered in energy, right, in that case here, and while only 1 electron's energy is raised actually. So we are raising the energy of only 1 electron and we are scaling down the energy of the 2 electrons. So the scaling down of 2 electrons is more favorable. This is the possible argument that can be given. Okay, so that's why this Jahn Teller elongation would be there, and in the elongation this option number, answer number, actually this option number 3 is the correct answer. Okay, now so this was the sum, these were the some problems actually which has been asked in the CSIR net examination. You can do the practice by your own, but you can see here, see now the question comes, how we can determine whether actually this static or dynamic Jahn Teller distortion is happening or not. So we whether the distortion is occurring or not, actually not a static or dynamic, but we can see how we can predict experimentally whether this distortion is happening or not. This is again this can be very beautifully explained by taking the electron spectrum of your complex. Say for example, if your complex is there and we are assuming no distortion, perfect octahedral geometry. So if you have electron here, so if you supply energy, then the electron would jump from here to here, right? And when coming back, it only one transition is there, or for one transition you will have only one peak in the spectrum. Whenever you find only one peak in the spectrum, that means no distortion is happening here. Okay, now say for example here the distortion has taken place. If the Jahn Teller distortion is taken place and this, these orbitals now they have splitted one, right? So during splitting, what can happen? If electron is present, it can jump from here to here, it can jump from here to here. So it can come back and it can again come back. So how many peaks I can expect? So I can expect 2 peaks in that case. That means the peak is splitting. So whenever you have the 2 peaks, that mean the splitted peaks in the electron spectrum, then you can say, okay, this distortion is taking place here. And if you are finding only one peak in the spectrum, then obviously no Jahn Teller distortion would be there. So this is one way of identifying it, right? So see, at low temperature, complexes having T2G orbitals gives 2 peaks. So T2G is having, see, whenever you have the T2G orbital and they have the electrons, so low temperature they will give actually the two peaks, but if you raise the temperature they will give a sharp band. So it is temperature dependent. So you can also identify whether the distortion is dynamic type or your say static type, right? If it is a static, then there would be no change in the number of the peaks, but if on increasing temperature your peaks, two peaks are converting into a band type of things, then it would be dynamic one, the weak one actually. Okay, now you can see here this was the question asked in the GATE 2010 examination, right? The DD absorption band of this is split. Okay, see this iron you can take here. If you take this iron 2 positive, iron 2 positive means iron is actually 26, so it will have 24 electron. 24 electrons means it is 3d6 system. Whenever the 3d6 system is there, so you can have this situation, okay, and your water is the weak ligand. Weak ligand means high spin complex 1 2 3 4 5 6. So Jahn Teller distortion would be there and weak Jahn Teller distortion would be there. Okay, weak Jahn Teller distortion would be there. So your answer obviously would be the C1. Presence of octahedral geometry cannot be your answer. Static Jahn Teller distortion cannot be your answer. Okay, because in the static you have to have strong ligand. It is a weak ligand actually. Okay, and for strong Jahn Teller distortion, this EG should be non-degenerate. Also, EG should be degenerate, but it is non-degenerate. So it is actually the third, this one, right? So this is how you can solve the problem based on this. Now very quickly, I'll explain the consequences of the Jahn Teller theorem, which is very important, right? So you can see here these all are the bivalent metal ions. This is actually Irving-Williams series. So if you take the bipositive ions and include, see, along with this alkaline earth metals, if you include your first transition series metals in the bivalent stage, then you will find your copper complex are having actually the extra stability. We are not including zinc here. Zinc is having the highest stability, but among these you are see manganese and iron 2 and cobalt 2 and nickel 2, then copper 2 is actually highly stable if the ligand is given. For all four, see this one, this one, this one, any metal, if have the same ligands, for the same ligands, then your copper complex would be the strong one. And this is actually can be explained due to the Jahn Teller distortion, right? Because in Jahn Teller distortion, copper 2 complex, you know, it is the 3d9 system, right? And 3d9 system, they will show the strong Jahn Teller distortion, and due to this Jahn Teller distortion, it is having the higher stability. Okay, now say second example, you can see here this molecule tris ethylene diamine copper 2 ion, right? This is ethylene diamine, this ethylene diamine, 3 times they are present. Coordination number is 6 because it is bivalent. Sorry, density is 2. When the density is 2, so one ligand is counted as twice. So 2 3 is 6. Coordination number is 3. This complex is actually the unstable. I have written here. Why unstable? You know, this is copper 2 complex. That means D9 system. It will have the strong Jahn Teller distortion. During this strong Jahn Teller distortion, this elongation would occur. And when the elongation would occur, then there would be high strain present in these two bonds, axial bonds, right? These are the big chain here, CH2 CH2. So distortion would be there. So strain would be there due to this Jahn Teller distortion. These axial bond would have the strain, and due to this strain, this would be unstable. Okay, so this is the one consequence of your Jahn Teller distortion. Okay. And then see, if you have two isomers, the same copper 2 complex D9 system, high Jahn Teller distortion would be there. But you can see here a transform. This is your transform where two ligands are transly occupied, right? So this is the stable form. This is trans I am writing here, and this is the stable. Why? See, because these two ligands are there, so there would be no strain. If elongation would occur, so it will occur easily. There would be no strain in the system actually. But if you make the cis, this is the cis isomer, then again you can see these two are present in the axial position. So this elongation would cause a strain. Due to this strain, this is less stable. This is another consequence. Okay, very important to note that. And then the next one, you can see here, this is your say KCuF3. This is actually your cubic, quasi-cubic type of the complex. See, don't confuse in this in this particular one. So you can have the confusion CuF by viewing CuF3, coordination number is only 3. So it is actually the quasi-cubic type of the structure, and in this structure, two copper, see what will happen. See, two coppers would be there, and then you will have a 3 here and 3 here, so they will form a quasi-cubic type of the structure. So in that case, two copper fluorine bond distance on the z-axis are 1.96, rest 4 are 2.70. So that means these are axial bonds are shorter and equatorial bonds are longer. Obviously it is Jahn Teller compression, right? So due to Jahn Teller compression in this particular compound, the two axial bonds are actually having the shorter bond length, while rest all are having longer bond length. See, if someone is interested to know the detail of this thing, so I am giving you the link here. This is the physics revision B52105. This is the paper published in the 1995, and this is the link. If you type this link in the Google, then you can access this paper and you can go through the details if you want, right? And last, I can go for this one. Say I have gold 2, copper 2, and silver 2. I have these ions, all are the D9 systems. If all have the D9 system, then all should have the same stability. But it is observed that your copper 2 and silver 2 are very stable, but your gold 2 is not very stable. It easily undergoes the disproportionation reaction. You know what is the disproportionation reaction? Disproportionation reactions are those reactions in which the same species undergo oxidation as well as the reduction. So gold from 2 positive to going 3 positive, it is oxidation, and again it is going from 2 positive to 1 positive, it is reduction, right? So this is disproportionation reaction, and this disproportionation reaction is explaining that this gold 2 positive is not very stable, right? Why this gold 2 positive is not very stable? The answer lies actually here. If you take first, second and third transition series, right? So whenever you move down the group, so crystal field splitting would actually the increasing. When the crystal field splitting would increase, so delta value would become very, very high. Due to this high delta value, high destabilization would occur for dx square dash dy square. So this would go up, right? Again, I can this one, right? This can go up. That means tetragonal elongation would be there, right? So when tetragonal elongation would be there, so due to this elongation, this complex would be very, very reactive, and it is easily undergo the disproportionation reaction, right? Extremely reactive, gold 3 positive. While see, you can see it should be octahedral, right? But when this convert into this one, it under see Au3 positive is square planar complex, and Au positive is the linear complex. So this is another consequence of your Jahn Teller distortion, why gold 2 positive is very much reactive when compared to the copper 2 or the silver 2, right? This again explained by using the Jahn Teller distortion. So guys, this is all about your Jahn Teller distortion. So actually I plan to solve a few more problems based on this, but the length of the video is actually has increased pretty much, so I'm not solving the problems now. Say if time permits, right? Not necessary, but if time permits, I will solve some of the problem based on this. So for time being, I'm signing out. So if you are liking the lecture and if you are watching the video for the first time, or you are a regular viewer but haven't subscribed the channel yet, so kindly subscribe the tetrahedron chemistry classes and do share your with your friends also. Thank you very much.